to, with functions of one variable, being able to take second and third derivatives and basically higher order derivatives. And we can do the same thing with functions of more than one variable. Let's just suppose I have f of xy equals e to the xy. Okay. Now, there are two first partial derivatives if it's a function of two variables. Obviously, for functions of three variables, there are three first partial derivatives. So I would have f sub x, or equivalently the partial of f with respect to x, and that would simply be y e to the xy. That's a quick application of chain rule. The derivative of the exponential function is itself, and then the derivative of the inside part, we're of course treating y as a constant. So the partial with respect to x of x times y is that constant y. Similarly, f sub y, or the partial of f with respect to y, would simply be x e to the xy. Now you'll notice both of these first partials are themselves functions of two variables. So each of them is going to have two partial derivatives. So what that means is that my function f is actually going to have four second partial derivatives, because I can take the first partial with respect to x, and then the second partial with respect to either x or y. Or I could take the first partial with respect to y, and then the second partial with respect to either x or y. Okay. If I then wanted to take a third derivative, there would actually be 8 of them, because for each of the four second partials that I got, I could take its derivative with respect to either x or y. So for a function of two variables, if I wanted to talk about the kth derivative, there would be 2 to the k versions of that I could have. Wow. Okay, so let's just calculate all four second partials for this particular function. And as we do that, we'll talk about the notation for things. Okay. So if I wanted to take the partial with respect to x over the partial with respect to x, so I'm taking the partial again with respect to the same variable, I would denote that as just f sub xx, okay? Or equivalently, what I'm doing is I'm taking the partial with respect to x of the partial of f with respect to x, and just like with functions of one variable, I'm going to, even though this doesn't mean multiplication, I'm going to borrow my multiplicative notation here. So del f, I would write as just del squared f over del x, I would write as del x squared. Now, this is an abusive notation, because if this were pure exponential notation and this really meant squaring, I would be squaring the x but not the del. It's understood that this is one symbol, and this just means write it twice. Okay, so that's the notation I would use for that second partial derivative. Now, when I calculate that, I've got y e to the xy. Okay, so y is just being treated as a constant, so I'm going to get that constant times the derivative of e to the xy. That's going to give me an e to the xy, and then a second factor of y. Okay, now if I wanted to take the partial with respect to x, and I wanted to take the partial with respect to y of that, I need to be careful with my notation here. We've got f sub x, and I'm going to take the partial of that with respect to y. So if I write f sub xy, that means first take the partial with respect to x, then take the partial of that with respect to y. Now if I use the del notation, I'm taking the partial with respect to y of the partial of f with respect to x. Now on top, I can still borrow my multiplicative notation. Del f becomes del squared f. On bottom, I really can't because I'm not repeating a symbol, so I just have to write del y, del x. Now notice we have to be very, very careful here. When I use the subscript notation, I wrote x and then y, reading left to right. If I use the del notation, reading left to right on the bottom, I've got del y and then del x. The order isn't consistent. What is consistent is that whatever I'm doing first is closest to the name of the function. Here, the name of the function appears furthest to the left. The thing I'm doing first is taking the partial with respect to x. In order for that to be closest to f, it has to be to the left. When I use the del notation, the thing I'm taking the derivative of occurs on the right side of things. So in order for the thing I'm doing first to be closest to that, it has to occur furthest to the right. Okay. So there is a consistent rule, but it's not a left-right rule. It's whatever's closest to the name of the function is the thing that you're doing first. And I think it's helpful to remember that this comes from applying the partial derivative operator to the existing partial derivative, and the partial derivative operator that we're doing last gets written furthest to the left. Okay, so if I wanted to calculate this one's actually a little bit tougher because now I have to use product rule, because I've got a product of two functions, each of which contains my variable y. So the partial of y with respect to y is just 1 times e to the xy, okay, plus then I would have y times the partial of e to the xy with respect to y. So that gives me e to the xy, and then times a factor of x, which I'm just going to write at the front next to that existing y. Okay, excellent. So those are the two second partials I get by taking the derivative of the first partial with respect to x. Let's now focus on the first partial with respect to y. Okay. So if I take a look at f sub yx, that would be the partial with respect to x of the partial of f with respect to y. That would be partial squared f over partial x partial y. Okay. So again, just getting used to the notation. You might have your preference for which notation you prefer. I would encourage you, as you're doing the homework in this section, to write out the problems using both types of notation, the subscript notation and the del notation, just so you get used to both of them. Okay. You may discover that you have an absolute preference and you're going to use one or the other almost all of the time, and that's totally fine. But you're going to encounter both types of notation, so you want to be comfortable with both. Okay, so let's calculate what this would be. So I'm taking the partial with respect to x. So it looks like that's going to involve a product rule here. Okay. So the partial with respect to x of x is just 1. So I'm going to get 1 copy of e to the xy plus x times the partial with respect to x of e to the xy, which is just e to the xy times y. All right, now, we've still got one more to calculate, but I just want to point out this one here and this one here, they're exactly the same. Now, the notation is important because it tells me the order in which I did things, and there are times when order matters. It appears that in this case, the order didn't matter. We call these the mixed second partials. The mixed second partials are when I take the first partial with respect to one variable and the second partial with respect to the other variable. And they turn out to be the same. Now, that is not coincidence. There's an important theorem that tells us under the right conditions, they will be the same. What I want to do right now is just finish calculating the fourth of the second partial derivatives that we have for this particular function. And then in the next video, we'll start with the theorem. It's called Clairaut's theorem, and I'll spell Clairaut's name because it's not intuitive. I'll spell that at the beginning of the next video. Okay, but our fourth partial derivative that we have would be f sub y. Y, that would be taking the partial of the partial with respect to y with respect to y. Okay. All right, and for that one, we don't need product rule. X is just a constant, so I get x times the partial of e to the xy with respect to y, which is going to be e to the xy, and then I get a second factor of x. Okay. Notice the non-mixed partials, although there was a similarity between them, they are not the same. And in general, we would not expect them to be. But the mixed partials, in general, will be the same. But we'll take a look in the next video at what the condition is for that to be true.